So this is a lot like the previous example. So this is Giancoli, chapter 14, number 4. We've got tea that we're pouring into a cooler cup, and we want to find out final common temperature of the tea and the cup when equilibrium is reached, assuming that we don't lose any heat to the surroundings. So that's a pretty good first order approximation. So we've got 200 milliliters of tea, and that turns out to be nice and easy. 200 grams or 0.2 kilograms of tea. That's going to be initially at 95 degrees Celsius. So there it is. You can see the pot here. And 150 gram glass cup. So this is 0.150 kilogram cup that we're pouring it into. That's at 25 degrees. And what else? And initially at 25 degrees. Okay, so now we want to calculate it. So what happens is we are going to have this tea, which is mostly water, we're going to assume, and the cup are going to be in thermal contact. So the hue that leaves the tea goes into the cup. So we want to find out the final temperature, equilibrium temperature, when the temperature is the same. And we assume there's no heat flow through surroundings. So that's what we'll be able to do. Now, what we know, it's a glass cup. So we've got this from the chart 14.1 specific heats. It's 840 joules per kilogram degrees C. So let's do the calculation for how much heat does the tea lose. Remember, its T initial 95 degrees. This one's T initial is going to be 25 degrees, so they've got different initial temperatures, but after a certain amount of time, we're going to have the tea and the cup both at the same T final, and that's the key we want to have, so that they're going to be at the same final temperature. So let's do this calculation. It's much like the one we just did. So, T, how much heat does it lose? Well, it loses the mass of the water times specific heat of the water times, what do we have, 95 degrees Celsius minus the T final. Okay, and how about the cup? So that's this one. How about the cup? The cup has a heat that it gets into it is the mass of the cup times specific heat of the cup times its temperature change, which is going to be T final minus T initial. Well, we're going to reverse it because we're going to heat it up. So we're going to find T final minus T initial. That's how much it heats up. So it I reversed it, but that's because we want to see how much heat it's absorbing. So how much heat that goes out of it is negative. So, okay, so hopefully you understand that. So we're going to equate these two temperatures. These two heats. CW, 95 degrees C minus T final. And we're going to do the same thing we did last time, is we're going to equate them. And we're going to solve for T final. T final minus 25 degrees. All right, so we'll multiply this out, and we'll find that MWCW times 95 degrees. Now I'm going to move this other term to the other side, so I'll multiply that after. And what I want out of this side is there's a minus 25 times this thing. I'm going to add that to both sides. MC CC times 25 degrees. That equals, now we're moving this final, so it's MWCW times T final plus this thing here. So that's MCWC T final. So you see that there's a common factor of T final. I'm just going to reverse this, and we're going to solve for T final. Hopefully I'm not doing this in too big a step. So it's this stuff, MW, mass of the water times the specific heat of the water times 95 degrees Celsius, plus the other thing we have, the mass of the cup, the specific heat of the cup, and that's 25 degrees. And we're going to multiply that, divide that by these two things, the mass of the cup, MWCW plus MCWC. Oh gosh, let's make sure we understand that. So this is the mass of the water, this is the mass of the water, specific heat of the water, mass of the cup, specific heat of the MW, oh my gosh, MCC, CC. Okay, got it. Okay, so now we're going to plug all our information in here, and I'll put the units in so we can see. Mass of the water, well, that's 0.15 kilograms. Times specific heat, that's from here. Okay, I'm doing the cup first, I guess. Let's do the 0.15 times the cup. Specific heat is 840 joules per kilogram degrees C. Now we're going to do the water. Mass of the water is, what do we say, 200 grams? So that's 0.200 kilograms times the specific heat of water, which we know is 4186 joules per kilogram degrees C. And we're dividing by, now you'll see the kilograms cancel here. And joules per degree C. And we're dividing by this thing, which is going to be the mass of the water. So that's the 0.20 kilograms times the specific heat of the water, 4186 joules per kilogram degree C. Plus, here we got MC, let's see, MC, so now the mass of the cup, 0.15 kilograms times, oh my gosh, can you follow this? That's the 840 joules per kilogram degree C. And that divides that, And what we have, and then we have the temperature. This is going to be times 95 degrees, thank you. And this one's, that's the glass, is 95 degrees, no, that's going to be, oh gosh, gotta stop. Okay, we're going to stop, well, let's keep going. This is supposed to be the mass of the cup and the times 25 degrees Celsius, so that's going to cancel as degrees Celsius, times, oh gosh, this is 95 degrees Celsius, that cancels that, and then we get this. Oh my gosh, can we get to this? Can we get the answer? Hopefully you see that this is going to be joules divided by joules, and this is going to be degrees C on the bottom. That will come up to the top, so we'll get a final temperature. Oh my gosh, we're going to follow this. Maybe we'll have to, let's see if we can push through here. 0.15 times 840 times the initial temperature of the cup. 0.2 the water times 4186, its specific heat, times 95 degrees. And we need to add those, and then we divide by whatever this is. This is going to be 0.2, 4186. That's the water, and that's 0.15. Enter 840 times, and we add those, and then divide the whole thing, and we get our final temperature, 85.8 degrees Celsius. So that's my final temperature for this combination here. Kind of got a little mixed up here, but I'm hoping that it's clear. So it's 85 degrees. So we started about 95. A little bit of heat went in to heat the cup, so they're both at 85 degrees at the end. Hope that's clear.